Working with some more spring problems, we're going to go ahead and start with a very light ideal spring with a spring constant of 2.5 newtons per centimeter, pulling an 18 kilogram box resting on a horizontal floor. The coefficient of static friction is given at 0.65. We're also given the coefficient of kinetic friction. We want to know how long the spring is just as the box is ready to move. That means it's already stationary. Because we're dealing with the box being stationary, we're going to be dealing with static friction. So let's start by taking inventory of all of our knowns and unknowns. We know the fact that K is equal to 2.5 newtons per centimeter. We're also given the fact that mass is equal to 18 kilograms. We're also given to the fact that the coefficient of static friction is 0.65, right? And that is a unitless number. We can then go ahead and use this information to draw our diagram, right? We start with our box, right? We know that we have a force down, that is weight, which we know is mass times gravity. We also know that this is a horizontal force, and it is resting on a surface. This is our normal force. We also know we have our force, our pulling force here. That is our spring force. I'm going to call SP. And then we have our force that is impeding our motion. It's keeping it stationary. This is our static friction. When we have all this information, we can go ahead and start building our equations. As we build our equations, we find out quite a bit of information going on here. All right. We find first the sum of the forces in the y direction give us the fact that our normal up minus our weight is equal to 0. Therefore, our normal is equal to weight, right? Or our normal is equal to mass times gravity. Right, so that's our y direction. Then we can go ahead and move on to our x direction. The sum of our forces in the x direction, all right, is our spring force minus our static friction. That is equal to 0. We have equations for both the spring force and the frictional force. So when we find that the spring force is in fact equal to the static friction, we can do a little bit of substitution and rearranging. We know that spring force is equal to Kx, so K delta x is equal to our frictional force, which is mu times n. We already found out the fact that our n is equal to mass times gravity, so I'm going to go ahead and substitute that right into our problem. Right? We were asked how long is the spring just before it starts to move, so we're looking for delta x. Therefore, delta x is equal to mu mg divided by k. All right, so we have that all set up there. Because we have that all set up, we can and we have identified all of our numbers, we can just start plugging stuff in. Our mu sub s, as we established, was our 0.65. Our mass is our 18 kilograms. Our gravity is 9.8 meters per second squared. All right, and this is over our spring force. All right, we know that a Newton has a particular definition. That definition is kilograms meters per second squared. All right, and we had newtons per centimeter, so then we end up with centimeters in the denominator. We went ahead and wrote out what a Newton actually is to make sure that all of our units are canceling properly. And we can see that they are, because we have the fact that we have kilograms over kilograms, we have meters per second squared over meters per second squared. We're left with centimeters in the divided by in the denominator, so that does put it up in the numerator. We plug that all into the calculator. All right, we have 0.65 times 18 18 times 9.8 divided by 2.5. We do get, or 2.5, we get 45.864. When we go ahead and round for sig figs, we do end up with 46 centimeters, right? And I can go ahead and my annotations are going to disappear for a second. And if I type in my 46 centimeters and hit submit, yay, we did it! We're correct. So here in this situation, now we are moving. So instead of static friction, we are dealing with kinetic friction. However, we're still in equilibrium because we are working at a constant forward velocity. If our velocity is constant, then acceleration is equal to 0. That means our net force is also equal to 0. So none of our equations have changed. As a result, we are looking at mu sub k is equal to 0.45. Plugging that into the equation that we found earlier, which was delta x is equal to mu times m times g all over k. So delta x is equal to 0.45 times 18 kilograms times 9.8 meters per second squared all over 2.5 kilograms meters per second squared divided by centimeters. Remember, kilograms meters per second squared is the definition of a Newton. Right? So when we do put all this into the calculator, we get 0.45 times 18 times 9.8 divided by 2.5 gives us 31.75. Centimeters. However, it asks for 2 sig figs, so we are looking at 32 centimeters. All right. The second question asks how long is the spring if the box pulls forward at a constant 2.75 meters per second. Well, did we factor in the velocity in part B? Well, no, we didn't. So does the velocity make any difference in part C? Well, it shouldn't. All right, so the answer you got for part B will be the same for part C. All right, so my annotations are going to disappear. Right, and we're going to see that we have 32 centimeters, like we calculated, and it's the same 32 centimeters for the next part.